So anyway, thank you very much for inviting me to this great opportunity. And I'm very happy with this event to share what we have researched so far. And today I'm talking about the system and applications of FPGA cluster ESPA for research on reconfigurable HPC. So I'm switching my pointer to raise a pointer. Yes, okay. So first of all, I would like to introduce myself and the organization where I'm working, which is Riken Center for Computational Science. Riken is the largest governmental research institute in Japan, and our center is for supercomputing. Our mission is to develop and operate supercomputer Fugaku, facilitate leading-edge infrastructures for research based on supercomputers, and conduct cutting-edge research on HPC. And as the leader of the processor research team, I'm conducting researches on exploration of future HPC architectures and advanced use of the present HPC systems, such as supercomputer Fugaku that we have developed in Riken. And we are hiring researchers. Please search RCCS 2105 and 2022. So the goal of my team is to establish HPC architectures suitable for post-Moore era, where the Moore's law is no more available. For this, we are conducting several research projects as shown here, while today's talk is about the first one, advancement of present supercomputers by a functional extension with FPGAs and system stacks. So this is the agenda of this talk, which contains introduction, motivation, and challenges of HPC with FPGAs, and ESPA, proof of concept FPGA cluster system, which is actually connected to supercomputer Fugaku for now. So let's begin with introduction. And for, as you know, for several decades, various supercomputers have been developed. And this graph shows their performance trends in the top 500 list, which is a ranking of HPL performance with distributed memory parallel computers. HPL means high performance linear algebra. This graph shows FLOPS performance since 1993 of the sum for all the top 500 systems in the list, the fastest system and the 500th system. So of course we are interested in the fastest system, and these are such systems in the last decade. In the latest ranking in November 2021, the supercomputer Fugaku of Riken was the number one with 442 petaflops, as well as other rankings of HPCZ, HPL, AI, and Graph 500. As you see, we can find some trends of HPC technology in this graph. So for example, recently more systems are relying on GPUs or accelerators. So in addition, the annual performance increase rate got slowed down around 2015. And this is probably because of the increasing difficulties in semiconductor scaling by Moore's law. Now we are projecting the performance of the future supercomputer around 2030, and its architecture based on the trends shown here. So, but there's another factor that needs to be considered more significant. And that is system power consumption, which is an emerging constraint of the total system performance. This graph shows the average power consumption of the system in top 500, top 10, sorry, top 50, and top 500 respectively. They are apparently increasing like this. However, it should be noted that the power consumption of the number one system has been drastically increasing. This means that we needed to increase the entire system power for higher system performance because improvement of the performance per power was very limited. The recent top systems consume tens of megawatts, while the supercomputer Fugaku consumes 28 megawatts for 442 petaflops with 7,630,000 cores. So can we keep increasing the system power consumption forever? The answer is, of course, no, because of the limited operational cost or electricity cost and SDGs. Actually, crude oil prices is now very troubling us, especially in this area. Yeah. So to know more about the reason for the limited improvement in performance per power, let's see the system configuration of Fugaku. The Fugaku is a homogeneous system with proprietary developed CPUs. By integrating more than 150,000 CPUs with a 60 torus interconnect, the system achieves the peak performance of 537 petaflops at 30 megawatts per consumption. Thus, this is not special case. The modern supercomputers are based on similarly on many core CPUs and GPUs in some cases. So, following question arises naturally: does the many core architecture scale forever at acceptable performance per power rate? The application performance of the many core architecture is modeled by this formula: number of cores by operation frequency by utilization of cores. So according to semiconductor scaling as shown in this graph of microprocessor trends in 40 years, we can project each of term in this formula as follows. First of all, I think we can expect a further increase of the number of cores on a chip due to the expected advancement of transistor structure, like FinFET to gate-all-around FET. So this graph shows the trend in transistor density, which is expected to increase some extent to worldwide. However, the operation frequency of each core cannot be expected to increase because of the end of Dinard scaling, which was already seen around 2005. So the remaining key factor is the utilization of cores for actual applications. So if we can have more cores on the chip, can we achieve higher performance by improving or keeping the high utilization of cores for applications? So the answer should be no, I think. And the many core architectures is difficult to scale further. And this is a figure of a single core, and its performance is already difficult to scale, as you know. This is because of extra hardware required to boost instructions per cycle, such as branch prediction hardware and an out-of-order mechanism. Since we need to rely on this kind of inefficient hardware to boost performance, we can expect more improvement of single core performance and performance per power. So, in the many core processor, we have multiple cores connected by a network on chip and with a shared last level caches. The entire performance doesn't scale even if we could have more cores. And this is because non-scalable network on chip and shared last level cache. Also, increasing latency in writing and reading shared caches makes the data movement among cores a bottleneck, and resulting in the less efficient parallel computation with many cores. As a result, no more performance improvement is expected, as well as no more improvement in performance per power in the case of many core architecture. So I believe that custom data for computing solves the problem where computation is performed by customized circuit pipeline with directly connected operators like this. With the custom data for computing, we can have efficient hardware tailored for target problems. Due to the pipelining and data flow computing model, we can easily achieve a scalable throughput with more parallels. In addition, we can have efficient and direct data movement among operators, which is optimized for fine grain. So, and I think that FPGAs are a good platform for now for custom data flow computing. And the state-of-the-art FPGAs have capabilities of high performance operation or computation, high bandwidth external memories, and ultra high bandwidth on-chip memories, and very fast inter-device communication, as seen in Stratix 10 FPGA specs. Furthermore, the next generation FPGA is going to have more advanced performances. And more specifically, I think FPGA is an attractive device not only for computing, but also for data movement, which is indispensable for scalable HPC systems. However, we still have several challenges for HPC with FPGAs. So in our project, we listed up challenges as these requirements for our prototype HPC system with FPGAs. So requirement one is interoperability with various HPC systems. This is necessary for us to easily extend an existing system with FPGAs. For example, the supercomputer Fugaku. Requirement two is flexibility in using FPGAs. In the case of large system where multiple users share FPGAs, it's necessary to utilize FPGAs without constraint of resource allocation. So requirement three is a platform with sufficient customizability. We need to develop a system on chip or FPGA shell with software abstraction layer for higher productivity. So at last, the requirement four is techniques for performance scalability. We need to develop low latency and high throughput communication infrastructure for scalable computing with multiple FPGAs. So for a proof of concept system satisfying these requirements, we have developed an FPGA cluster system, which is named ESSPER. ESSPER is the abbreviation of Elastic and Scalable System for High Performance Reconfigurable Computing. And this is an experimental prototype for research on FPGA-based functional extension of existing HPC systems, such like supercomputer Fugaku. And actually, ESPA is now connected to Fugaku, and we can use these FPGAs from Fugaku computing node. And this is another photograph with me taken when we connected ESPA to Fugaku 2 years ago. ESPA is located in a different server room from Fugaku, and we needed to use 100 meter optical cables. So we installed an extra InfiniBand NIC into Fugaku for connection between Fugaku and ESPA. And actually, we started this project 4 years ago as a part of Fugaku development project. And although there were a lot of difficulties in solving both technical and strategic issues, or political issues, but finally we made it successfully. So this is an architecture of ESPA, which is for the technical investigation for functional extension of Fugaku with FPGAs. So here we have FPG cluster here, and Fugaku here, and the bridging network connects the FPG cluster with Fugaku. And this is an actual structure of ESPA, which is composed of an FPGA cluster part with 8 servers and 16 FPGA cards, and the bridging network for connection with Fugaku, and the other services such as FPGA compiler and simulator, etc. For bridging network, we use 100 gigabps InfiniBand switch. So this slide shows the system stack of ESPA. So we have FPGA device in the bottom and the system on chip on the top of it, shown as AFU shell. Then we have multiple layers of system software from PCIe driver for FPGA and resource manager. And some of them are already developed and under operation, but while the other parts are not yet and still open for joint research. So first of all, I would like to explain these layers, which is a SoC, system on chip, or FPGA shell, and its object class library for hardware abstraction. So they correspond to the requirement 3, platform with sufficient customizability. In ESPA, we have 16 FPGA cards installed on 8 servers, and we adopted Intel Programmable Acceleration Cards PAC D5005 because of its state-of-the-art Strat10 FPGA from Intel and an open source driver. So the specification of the board is shown here. We have 760 floating-point TSP blocks, 4 channels of 8 GB DDR4 memories, and 2 ports of 100 Gbps network port, QSFP28. On the FPGA FIM, FPGA Interface Manager is implemented by Intel as a fixed hardware region, including interfaces for DDR4 memories, PCI Express, and networks. In the FIM, we have a reconfigurable region called Acceleration Function Unit, or AFU, where we can program user circuit repeatedly. And in this AFU, we have implemented AFU shell, which is our own system on chip common for various applications. And this is a block diagram of the AFU shell. And in this AFU shell, we have direct memory access DMA modules to read and write data streams with DDR4 memories and host memories. A 4x4 crossbar to route data streams, crest-based flow controllers for inter-FPGA network interfaces with serial write 3 IP cores. In AFU shell, users can freely embed their own computing cores. For HLS-based core, we embed it to be attached to the memory bus of Intel Avalon MM memory mapped interface, while a stream computing core can be embedded by connecting it to the crossbar with Intel Avalon stream interface. For programming, we provide several approaches. First of all, we need to implement a computing core or system stream computing core for applications. The computing core actively performs computation by reading and writing data with DDR4 memories. On the other hand, the stream core works passively by processing an input data stream generated by DMA modules. Then we can use these ways to program the core, including HLS, HDL, and DSL. We are recommending users to use HLS to program applications because of its productivity, while HDL is also available, especially for implementation of FPGA overlay hardware. So these approaches are a bit low level, however, more flexible than OpenCL, for example, and its DSP. And we can customize anything completely with our infrastructure. So next, I would like to talk about the inter-FPGA network with virtual circuit switching over Ethernet, which corresponds to the requirement 4, techniques for performance scalability. For 16 FPGA cards in ESPA, we have designed 2 different types of inter-FPGA networks, which are these 2 types. So one is direct and the other one is indirect network. The main advantage of the direct network is the small overhead with lower latency, while the disadvantage is the low flexibility. On the contrary, the advantages of the indirect network are high flexibility and scalability, and the disadvantage is relatively low high overhead or higher latency. So when we consider a large system with a lot of FPGAs shared by multiple users simultaneously, flexibility is very important for operation and for efficient use of FPGA resources. Let's assume that the case where we have, for example, 10,000 FPGAs and the user uses only 100 FPGAs of them. In the case of direct network, we cannot guarantee the full torus topology for the partial use. On the other hand, the indirect network allows us to use any FPGAs equivalently in the system. So due to this flexibility of the indirect network, we have developed the virtual circuit switching network called VCSN over Ethernet to achieve both flexible and easy to use network for FPGAs. So using VCSN, we can configure arbitrary topology with virtual links between FPGAs like this. So this is achieved by the Ethernet frame encoder and decoder, which convert the data streams into Ethernet frames. and multiplexers and demultiplexers to provide virtual ports to user logics. By writing destination addresses to the frame encoder, we can reconfigure virtual links with arbitrary topology. So by this, user logics can use the virtual links as if they were physical point-to-point connection between FPGAs without complex control of an Ethernet core. And we can dynamically change the virtual topology as required. The pros of this approach are flexibility and scalability, or availability with a commercial cutting-edge technology of higher throughput, such as 400 gigabps Ethernet. The cons are the extra latency for processing Ethernet frame. To demonstrate the approach of BCSN, we have implemented its A-field shell for our FPGA card, which is shown in this right side. And with this, we can configure, for example, a virtual two-dimensional torus network as shown here. Although the A-field shell is still under test, but now it works at least for evaluation cases. So this is a preliminary evaluation result regarding throughput. We have compared the two types of networks, direct connection network, or DCN, with physical point-to-point connections, and VCSN, using 100 gigabps Ethernet. This graph shows the measured throughput against the increased data sizes. And because the P2P latency of VCSN is 551 nanoseconds, that is higher than 490 nanoseconds of DCN, the throughput of VCN rises slowly. However, and interestingly, the VCSN has higher maximum throughput against DCN. This is because the jump frame of Ethernet, which is more efficient than the inter-CRI3 protocol used in DCN. But anyway, now this works well, and we are evaluating performance difference of collective communication between DCN and VCSN.
Kentaro, just to remind that you have 5 minutes.
Okay, got it. Okay, that's enough. Thank you. So next, as a solution to requirement 1 and 2, interoperability and flexibility in use FPGAs, we have developed a software-bridged FPGA driver over InfiniBand network and FPGA resource management. So in the system stack of ESPA, they exist just above the PCI Express driver for the FPGA shell. Yeah. So when we use FPGAs in ESPA from Superconductor Fugaku, we need to do it remotely via InfiniBand network. For this, we have developed a software-bridged driver called Remote OPAE. So OPAE, a Open Programmable Acceleration Engine, is a local FPGA driver, which is provided by Intel. Remote OPAE provides transparent access to remote FPGAs with the same APIs as OPAE's API. Remote OPAE is implemented as a software bridge over InfiniBand network. So this shows the system stack on the FPGA server. On the top of FPGA board, we have an FPGA driver and libraries, which are of OPAE. User applications are running here. So to achieve remote access of FPGA boards, we run remote OP demo on the FPGA server, which is locally accessed FPGAs with OPAE. Then a user application running on another server called remote OPAE APIs, identical to remote OPAE's APIs, to remotely utilize FPGAs through InfiniBand. The requests from the user application are bridged to the remote OPAE daemon, and the daemon accesses the FPGA by proxy. So with remote OPAE, we can use any FPGAs in the system via network as if they were locally installed. So the advantages of remote OPAE are high flexibility and extensibility as software-based resource disaggregation. As I mentioned, it allows transparent access to remote FPGAs, and it allows flexible resource utilization in a system like this. And we can use any available FPGA resources in the system. In addition, we also have the advantage of interoperability and extensibility. Now, vendor or ISA independent operation is possible for different architectures such as ARM-based architecture of Fugaku. So let me quickly introduce what we are doing with our system as research. So here we have several projects under joint researches in our team. and from hardware development to application development. At hardware development, we are researching CZRA overlay with our cluster ESPA, and the other university is collaborating with us to develop AI engine as FPGA overlay called RENA, shown in this figure here. And as software development, we are also researching remote procedure code for remote FPGAs. And Tohoku University in Japan is also developing their own SQL implementation on Fugaku to control FPGAs. And as application researches, we have several ones. For example, Bayesian network analysis, 3D FFT, full simulation, and hardwired machine learning or some kind of things. So this is the last topic of my talk, and for future prospects for reconfigurable HPC. So now we are in the golden age for computer architectures, and there are a wide variety of processors for, especially for AIs or data processing, based on reconfigurable and data flow architectures. And I think this kind of reconfigurable and data flow based architectures would be still promising in the future, including CZRAs. However, backward compatibility is also required, especially for programming languages and ecosystem. So we need to carefully design the system with the sufficient support by architecture, coupling CPU and different accelerator architectures for various type of workloads, and compiler and system software for seamless usages of different architectures, including CPUs and data flow-based accelerators. So let me conclude my talk. Our goal is to explore new system architectures for reconfigurable HPC, and I introduced our project ESPA as a proof of concept of the system for interoperability and flexibility, platform form customizability, and scalability. So in our future work includes more applications with multi-FPGAs, new shell with HBM2-based FPGA, resource management, and task scheduling for Fugaku. And we are expecting collaboration with you. So this is my talk, and thank you very much for your attention.
Thank you very much for the presentation.